morning, everyone. So first, thanks for everyone who arrived early. No usual to start 9:30, but for a good cause for outreach, because Fernando also speaks at better break, 5 later, midday. But so as we know, today we have a very nice guest, Fernando Rosas from the University of Sussex. He has a very interdisciplinary training from bachelor's in music to mathematics and engineering and neuroscience. So it's a very good mix. And his main focus in the last year was on emergence and neuroscience. Maybe he will talk about his new baby, emergence and AI. But I don't know, that's up to you. He's a frequent guest, like he came to our ears and did many times. So it's always nice to have him. Thanks so much. The floor is yours.
Thank you.
Can you press the OK button?
Thank you.
Well, thank you very much. I'm really happy to be here. Thanks for the invitation. And I'm very excited to talk about emergence with the emergence people. So this is great. And my plan today is that I have this sort of idea that most of us, we start thinking emergence is one thing and we just need to grab it. We just need to find the right formula or the right formalism, and that's it. And different people find different formalisms, and then naturally they start fighting because which is the right, which is the wrong one. And I'm starting to have this strong belief that actually maybe we're all right in different ways, meaning that there are different phases of emergence, in the same way that complexity. In the beginning, we all thought that complexity was one thing, but after a little bit, we realized that complexity can be, incompressibility, hierarchy, a number of things. So the same with emergence. And that's the main idea I will try to communicate with this presentation. So before you know super well what emergence is, but to give a bit of a concrete feeling, we all have experience seen maybe this flocks of birds in the way they move and how there seem to be sort of this macro thing with its own shape and its own direction that of course supervenes on the birds. So we are not saying there is a substance that cannot be found in the birds, but we think that the whole thing has something more than parts, right? So it's sort of one very basic intuition, and the other one is this video that I found in internet a long time ago. Unfortunately, I don't know what is the identity of these little animals, but you can see how they work together. So, if they would be facing the dog separately, they would definitely don't have the same chance to deal with the dog in this way. But because they work together, they have causal effect in the world. They're making a difference, right? And it's very, you cannot deny it. You cannot say this is a way of talking. No, these people are achieving a different objective because they're working together. So this is the type of thing I'm thinking how to formalize. And I start from the point that we have an intuition for this. We have a feeling like, oh, there's something interesting here. And we just kind of point our finger, but we have this sort of basic intuition of what it is. So for today, I will first introduce some very general ideas to sort of set the boundaries of the discussion. And then the plan is that I will present two approaches to measure emergence that I have been working in the last years. And my intention with this is to show how different they are. I'm not going to argue that neither of them is the right one. On the contrary, I will highlight how this is good for this and how this is good for this other thing. And then at the end, I will summarize some ideas. So to start, when talking about emergence, I find very helpful to start fixing a bit of metaphysics. And there we have the intuition from reductionism that whenever you have a system is basically a machine made of parts, and the only difference between a duck and a brain and any other system is the number of parts and the size of the parts. So the main magic of the human brain would be that there are so many neurons and they're so tiny, but that's it. They're just parts interacting with each other the same way than a windmill or any other system. And I think this is a position that is very hard to argue against. I don't think it's possible to say this is wrong, but maybe we can say this is not very productive. So another alternative is to say, well, even in the eventual case in which we have sorted particle physics, we sorted, we have everything, we understand how superstrings work or whatever. Can we predict communism or social phenomena that happen at a very high scale? And emergentism would say we cannot do that. But the question is why we cannot do that. And then there are two possible answers. One is that this impossibility holds in principle. So you just cannot do it. It doesn't matter how much computational power you have, or how long you compute, how much data you have, etc., etc. You cannot do that. And the central claim here is that there are some big properties, some macroscopic properties of the system that have causal power that cannot be reduced, cannot be explained in terms of the causal power from the micro. Another possibility, a bit more conservative, is to say the impossibility holds only in practice. In principle, it could be done. So if we have enough compute and we crack the machine for a long time, we would predict everything. But in practice, we cannot do it because we're finite beings with finite resources. So it's a practical problem more than in principle problem. So we have these basic three positions. There are infinite more. This is a continuum, most likely not a one-dimensional thing. There are many instances. I'm just presenting this sort of to fix ideas of the types of discussions. So if we have these three options and we ask the question, is it possible for a macro level property to have causal power that is not reducible? These different people would have very different answers. A reduction would say simply not. This is just an illusion. And all these coarse graining levels is just a convenience of description, but nothing else. A strong emergentist would say, of course, yes, in some systems, and then the discussion would be which systems yes and which systems no. And then weak emergentists would say it looked like that, but actually not. But it's sort of useful and something in between. And the way I see this discussion is like this. So it's until we decide like very hard, like what is causal power exactly? Because causality is the type of thing that when you haven't thought about causality too much, it's like, oh, causality is simple. I press the button, light goes in. But the more you think about causality, you start going this rabbit hole, and it is very tricky what causality is. So until we don't fix what we mean with causality and what we mean with reducing, because what is to reduce causality is also not a straightforward concept. Until we don't decide these things, until then, the discussion, I don't think it makes too much sense to take it very seriously. I mean, it's interesting discussion, but it's very easy to disagree because we are talking past each other. Another question is, could we find a minimal model where we could reason about this grounded on a concrete system, and then we can have a discussion based on a specific instead of these very general discussions? And can we measure something? And my personal interest in this is that I would like emergence to be useful in experiments. So we have some experiment and we decide stuff about emergence from data, not from argumentation only. So my plan is the following. So I see in this spectrum these two extremes. So in one case, it's like emergence is anything that is crazy. If you can explain it, it's not emergent. And I don't find that very helpful. I find it a bit of a dead end. Then on the other hand, this explain away emergence, like emergence looks like, but actually there's nothing there. I also don't find it very, very helpful. I don't think that these are wrong positions, but I don't think they are very helpful. And my interest is in between. And I can see a continuum in between where it's like emergence, you put a little bit and you get a bit of out. And I can think of many different positions in this sort of compatibilist view of emergence. And my interest is to explore this space and to see what are the options and what are the possible stances we can take. And more concretely, the hope is that to have a framework that has some philosophy, but not too much, not too little, because we will need some, but that's a lightweight framework where the aim is not so much to convince you that the brain is emergent or anything else is emergent. It's more of a framework to establish hypotheses. So to be able to say exactly when I mean this system is emergent, what I mean is this. No, so to concretize things, to be more specific, and then in a way that then this hypothesis can be verified, hopefully with experiments. So we have a conjecture, I think the system is emergent. What I mean is this exactly. Then I do an experiment, I get data, and then I get a p-value, and then I say, with this confidence, yes. So that's the idea, to bring it to empirical science from this philosophical discussions. And And my point, to be clear, I don't think that philosophy is not helpful. I just want to complement all the philosophical discussion about emergence with stuff of this flavor. And in the rest of the talk, I will present two frameworks in which we can establish hypotheses and then verify them with data.
Yeah.
Yes.
So maybe you will discuss it in the rest of your talk, but how could you ever convince a reductionist in the sense that you could always do some experiments and a reductionist can always say, well, yeah, there is something we don't know yet, and you could never convince one, I guess. Like,
Yeah, maybe we can delay that discussion to the end, but the idea is that with these frameworks, when you go to a reductionist, you say, I say this is emergent, and what I mean is this. And you can be very specific, and the reductionist cannot say no, because this is what you mean, and the data say yes. And then maybe he can try to do gymnastics to explain that different way, but at least the discussion gets a bit more narrow. And when you see the type of things that I'm trying to frame in these formalisms, that maybe we can have a more concrete discussion on how this scenario could look like. So and now I will try to operationalize these ideas of emergence in different ways, and we will see how they look like. So first is this notion of hierarchy and computational closure, and then the second would be this whole minus part view of emergence. So let's start with the first one. And the first view starts from this intuition that the natural world is structured by layers. So we all know that, you have, in physics, you have like strings, and then you have quantum, and then you have classical. In biology, you have all these different scales that to some degree are independent. So when people study the brain, they don't worry too much about electrons. Well, they do, but a lot of the discussion has to do with firing and stuff. Or then when people do sociology, they study about social system, social phenomena, and sometimes they have to look below, but to some degree, they can do sociology at the level of sociology. So there is a degree of self-containment of different scientific disciplines, and I would say that's a datum that suggests that nature is structured in that way. So we have these levels of relative autonomy. And in parallel with that, we said we have this idea of abstraction. Like we think in terms of abstractions, and we have this idea that we have a concrete thing like this sphere of bronze, and we have the idea of a sphere, and we have the idea of bronze, and this has been a long discussion since Greece, but I have never seen a satisfying take on what abstraction means mathematically. And this becomes important with AI now, because with AI systems, with reinforcement learning, we wonder if these systems have abstraction, do they have a notion of the world where they are acting, et cetera, et cetera. So this is this type of thing I will try to go to capture what does it mean, these abstractions on these levels. And another related point that brought me to this is this discussion in neuroscience about, is the brain a computer or not? And as you can see there, maybe it's too small, but I can send you the slides later. There are papers saying, of course, the brain is a computer. And then there are papers saying, of course, it's not a computer. And people fight very strongly. And my personal take on the discussion was like, under some definition, it's a computer. Under some definition, it's not a computer. What are we learning, really? And I couldn't see so much. So from there, I start wondering about, okay, what is software? So we're shifting a little bit the question. So when I have my laptop here, my laptop is a physical system running on, Schrödinger equations, or who knows, but some physical dynamics, but is running some code. So let's say I write this Python code, super simple, A equals B 2, B equals 3, C equals E plus B. And if we print C, we know that we're going to get a 5. And we can run this thing multiple times. And the physics are going to be different every time you run the software, but the outcome of the software is going to be always the same, right? So it seems that there is some sort of levels at play, where at one level we have physics that is very messy, and every time you run is different. But at another level, you have this programming logic where things are stable. And you can run it multiple times and the thing will be the same. And you can run the same algorithm in a different machine where the physics is going to be different, but the algorithm is going to be the same. So that is and that has a flavor of abstraction, right? And even computer scientists speak about abstractions, etc. So that is the thing that I would like to put mathematics in. Now, for that, to start putting some math, we start with a system described at the micro level with full detail that is X, a different measure at different points of time. So we have a dynamic on X. And then we have a coarse graining function that in principle can be with a memory, but to keep it simple in our heads, we can say we're coarse graining just space. So we are less able to disambiguate different states of the system. So instead of seeing all the spins up or down, we can see an average maybe. It's like in thermodynamics. So now you have this coarse grained version of the same system that we call set. And set has its own dynamics that are inherited from X. And that is the type of thing we're going to think how X and set relate in different ways. And when can we say that set is sort of a software of X? That's kind of the question that we would like to answer. Now, when you start thinking of software on these levels, you start seeing everywhere. And these are different examples. And my favorite one is the toilet flushing. And let me try to convince you that the toilet is running software. So let's say you go to a toilet and you flush the toilet. So the water goes out. What happened next is that water started coming in, the water level start rising, and there is a floating device that at some point it will be pushed by the water level, and when the thing is pushed, then it's going to close the input, and then the water is not anymore coming in, right? So that is sort of a while loop. Like if while the thing is down, keep water, and while this is not anymore true, then you cut the thing. And that while loop, it will run the same, basically the same, every time you flush the toilet, even though the Navier-Stokes dynamics of the fluid are going to be completely different, right? So at that level, the mechanism of that is driving this refilling of the toilet is running as an algorithm with its own logic that is implemented on hydrodynamics, but as you see, the while loop is happening at a different scale. Another example, when you have a self-driving car, you have this car driving around the city, and it's having some cameras, and is making decisions based on the input data. And the car is made of strings and parts and whatnot. But to make the decisions about how to navigate is not measuring that level. It's measuring a much simpler coarse grain level of reality, and nevertheless is navigating more or less okay. And the same for us, like we are macroscopic systems and we navigate our world, but we have no perception of quantum mechanics or stuff. And we navigate fairly fine. And it's most likely that if we could see, quantum states, I don't know if we could navigate our world, our human world better. So in that sense, we are running on software too. So how can we frame, operationalize these ideas? So the first view, the plan was to start thinking how you can have a coarse graining that is self-contained, and what could that mean, and in what senses you could be self-contained. So the first approach to self-containment is about information and about prediction. So if you're familiar with information theory, the mutual information, shadow mutual information says how much information a variable has about another variable. So what I'm measuring here in the left is that we are going to predict the next state of the coarse grain, the level of the system, with the past history of the coarse grain system. So the bold letters are trajectories. So from -infinity to t, and then we are using this trajectory of this coarse grain level of description to predict the next coarse grain state. And on the right-hand side, we have the mutual information between now the history of the micro of the system and how much information that thing gives me about the next state of the coarse grain level. So basically, we are doing a comparison. We are predicting the next state of my system at the coarse grain level, either from the full information of the micro or from the coarse grain information. And in general, we will have an inequality there. So the prediction you can make from the micro information is better because you have more information. And in information theory, information never hurts. However, it could be that we have this special coarse graining such that this inequality turns into an equality. And that means that you can do optimal prediction from the macro. Put it differently, let's say I'm living in this macro world and I want to predict the next state of my world, and I do it based on my history as a macro system. And I can do, X, I can predict 30% of the variance or something like that. And then suddenly somebody offered me, like, would you like to pay like £1 million to actually make a prediction using your microphysics? And the question is, should I pay that money? Will my prediction improve or not? And if it will not improve, that means that my level is closed, it's self-contained. All the predictive information is already contained in the macro. And that is what that condition tells. And there's an equivalent formulation in terms of a conditional mutual information that if maybe you have seen it, this is called transfer entropy. And that will mean that there is zero transfer entropy from micro to macro. And this condition says that everything that can be predicted from the macro. So all the predictive information is already in the macro. And this is the notion of information closure. And so far, this is just a definition. Like coarse graining is informationally closed if these conditions are satisfied. Now, the next question is about causality. Like this is about prediction, but what happens now if we do an intervention? And the idea of causal closure would be every difference that could make a difference is in the macro. So if I want to control my system optimally, I could control it only from macroscopic steering wheels. And how can we formalize this? And at this point, the idea was to turn into a field called computational mechanics. Are any of you familiar with computational mechanics? No? Computational mechanics is this theory that starts from a time series X. And then what you do is that you do a coarse graining of the histories based on their predictive ability. So if you have histories like in the left that different histories, like let's say you have a binary process 0, 1, 1, 0, 1, 1, and then given the history, you see the conditional probability for what is coming next. And if you have two different histories that led to the same predictions, you say they are equivalent. So you coarse grain everything that you can coarse grain because their predictability is the same and nothing more. And you can prove that this is the optimal coarse graining in the sense that it keeps all the information, but is sort of minimal, but maximal at the same time. So this is the best encapsulation of the relevant differences for the future. And the beauty of this framework is that this leads to an HMM type of construction where the hidden Markov model is optimal in the sense that it has the minimum number of states such that you generate the observations. And the reasoning is that my data, X, that is what I'm measuring, I am imputing the smallest possible mechanism that could have generated the data that I'm observing. But this is the idea of the epsilon machine, is this sort of minimal mechanism that can generate the observations. And from this idea, and the basic idea that I will be using here, computational mechanics is huge field developed by Jim Crutchfield and others. And from here, I'm just going to focus on this idea of causal states. That is the coarse graining that keeps the differences that make a difference. And what I will do is to do a similar construction that, just for being funny, I call upsilon machine instead of epsilon machine, where you do the same equivalent class. So you say two trajectories of the micro are equivalent if and only if their conditional probabilities for the future of Z are equivalent. So you're not predicting X as in here, but you're predicting Z. And that's a little bit easier because you're predicting less things than before because you're coarse graining. And in general, the epsilon machine is going to be a coarser partition than the epsilon machine. So you keep less distinctions, but you keep the distinctions that are relevant for the macro. Right. So, and the idea with the epsilon machine is to isolate what are the differences that make a difference for the future of the macro from the micro. So if you want to steer optimally the macro, what you need to keep separated, what you need to be able to distinguish or control is the states of the epsilon machine. And with the epsilon machine, we can come with a definition that say a macro process is causally closed if its own epsilon machine is equivalent to the epsilon machine from below. And epsilon is because of underlying. So, and
So
what
the epsilon machine at the macro level.
Yes. So basically here there are three machines.
Yeah,
You have the epsilon machine of the micro with the micro, that is everything that makes a difference. You have the epsilon machine with the macro with the macro, and then you have the epsilon machine that is going through. And the question is, under what conditions the epsilon machine is equal to the epsilon prime, that is the one on top. And of course, in general, this is not going to be true. And you can have really strange things happening. Like there are some coarse gradings that make the epsilon machine of the macro much bigger than the epsilon machine of the micro. And that means that you suddenly became sort of blind, and then your world is much more confusing than before. And because of that, everything is more difficult to predict. Yes.
Do you call two machines equivalent if they have the same states, or do they also need the exact same transition?
Yeah, you need to have a function that maps the states between.
That also.
Yeah, the condition is fairly strong. So they need to be sort of synchronized.
Yeah.
So basically, you say the states are the same, but you are just labeling differently.
Right.
So this is the definition for causally close. A question was, what is the relationship between informationally close and causally close? And to my surprise, I was not expecting this. We found that they are equivalent with an important caveat, that is, under the condition that the microscopic system is fully observed, in the sense that it has all the causal relationships that make so for physics, this is the natural choice, like X is the whole system that you're studying, and then it's close in the sense that everything that is relevant is being accounted for, and then this equivalence holds. If you have a micro that is more like, in biology or social science, it's very common that what you're measuring is not all the causally relevant elements. And then causality and prediction is a bit different, and this equality don't hold. But for the purpose of this first effort, I focus in the case where X is fully observed, and then this is an equality.
I have a question about this.
Yes, please.
So the index T you had was always time, right? So you have some kind of time error.
Yeah.
When you talk about causality, you mean interventional causality in that sense?
Yes.
And causally close means you intervene on microstates. Is that what you're saying? You're saying basically if microstates only affect macrostates, then the same intervention on macrostates gives the same.
Yeah.
How do you formalize this? It was kind of implicit.
So basically, if you're familiar with the parallel interventional account, what you're saying when you say the microscopic level is fully observed, you're saying that the conditional probabilities of X are the artifacts are the equivalent as interventions. So you will not make a difference if you intervene or if you just observe the conditional.
Okay, and the relation between the micro and the macro states are here.
So here you're doing two partitions of the you're doing three partitions actually. So no, actually two. So here you're doing a partition of the past of the micro based on the predictive ability for the macro.
What do you mean by partition? That's not that clear.
So you have different histories.
Yeah.
And you say that you are going to put them in the same equivalent class if their conditional probability for the future of the macro is the same.
Oh, okay.
And if that holds, then you say, I will stop separating them. So you coarse grain them.
Okay.
And you find a partition, a coarse graining, that you are confusing all the histories of the micro to the degree that they lead to the same outcomes. And then what you could think of is you have different interventions that could be historically, it could be I intervene first and then, so it's a sequence of interventions. And I say two interventions are equivalent if they lead to the same outcomes. But you're starting from all the interventions you could do if you intervene at the micro, you coarse grain those and you end up with equivalent classes of interventions. And then you do the same story, but with interventions at the macro. And then you compare these two equivalent classes.
Okay.
And if there is if they are equivalent, the two partitions are basically the same, then we have causal class. Is it clear?
Yeah,
Sorry, I still did not understand when you say they have the same microscopic history. You mean that the states are the same? Is the same microscopic states in the history, or is it that the transition kind of probabilities are?
So when you do the epsilon machine of the macro is a coarse graining of the micro. So that's already a coarse graining, right? And then you're coarse graining again in terms of when you do the epsilon machine of the macro. So
No, but when you say that the microscopic states in this story, the x1 to xt, when you say they are equivalents, when you say x1 to xt, is this like actual states? Like, is it microscopic states?
Yeah.
So if I have a Markovian process, for example, then they would be all equivalent if they finish on the same xt minus 1.
If you have a micro that is Markov, then what you do, you see the different transition probabilities,
yeah,
and you say two states are equivalent if all the transitions are the same.
But if I have a trajectories and on the same state at xt minus one,
Mhm.
then the next state only depends on xt minus one.
Yeah.
So then it doesn't matter what I did before. Every trajectories that finish on xt minus one, on that same xt minus one will be equivalent. Do I understand this properly?
No, so you take all the trajectories, but as you say, in a Markov process, you will not consider the long trajectories. You're just going to consider the last state. And then you check all those last states. So you basically you check the phase space. And each point of the phase space is going to have a different vector for the next states.
Okay, so it's not just a microstate, there's a microstate with the process.
Yeah, with the
Okay.
transitions. And you are coarse graining if the transition probabilities are the same.
Okay.
Any other question?
Oh, I have some sort of bookkeeping question about the next slide. So you call it here, is this your theorem or is this something that is well known in the literature? Or...
I couldn't see it elsewhere.
Okay,
So
yeah.
Mm.
And this is written down somewhere, including complete proof and then.
Yeah.
Okay, great.
Yeah. In the here. That's a preprint. I'm very happy to send the slides after. And that's a preprint, and that the preprint is written in a funny way. So it's first written for humans, like in a very friendly way, and then this appended like all the theorems. And it's basically two papers, but it's for different audiences. So one is for a friendly version when you explain this, and then all you have theorem proof, counterexample, blah blah.
So does this depend on the coarse graining mechanism?
Yes. So when you have a coarse graining, it could neither be causally closed, neither informationally closed. So there are specific coarse graining that satisfies this. And what this theorem says is that if the coarse graining satisfies one, then satisfies the other. But it couldn't not satisfy neither. And in a way, it's a good question, because in a way, this theory is trying to say what are good coarse grainings, and what are abstractions, and what are the software levels of your physical system.
So you only have to worry about satisfying one and then you get the other.
Exactly.
So do you think if you apply the classic statistical mechanics problem like gases to
It's coming. Yes.
It's somehow to predictive information because you're looking at how much all the trajectories that your process can create up to a certain point can predict the future points.
Mhm.
And then you're looking at basically how many of this type of process can produce the same points with this period.
So the second condition is about prediction.
Mhm.
And you're asking prediction from the same level or from below. And you're comparing the predictive power of both.
Because there is something called predictive information that's you don't know.
No.
And going back to what Claire asked about Markovian system that simplifies the thing, is more treatable, or
But yeah, I mean, in the sense that to get the epsilon machine of a Markov process is fairly easy. In that sense, yes. But one of the powers of the system, of this framework, is that you can deal with non-Markovian without any problem. And we will see more about it in a little bit. So now let me come to the more exciting part, that admittedly, this is the more new part that even for me is a bit, I'm still sort of digesting exactly what does it mean. So part of the effort was to give a computational explanation of what emergence means. And emergence understood as self-containment. Because I've been doing information theory for a long time, and you end up with these quantities that are a bit of a black box. And it's like, oh yeah, I get a good number, 0, not 0. But sometimes you don't see so much how the system is working internally. And my hope was that putting computational mechanics in the story could give me a bit of more strong grab on how this works. And the beautiful thing about computational mechanics is that you have this epsilon machine that is often seen as a HMM, meaning this sort of mechanism that is generating the observations, but is that you can also do, you can see the same mathematical construction as an automaton from theoretical computer science. I don't know if you are familiar with this, but in computer science, you have these machines that recognize languages, and then you have regular languages, and then you have different classes of languages according to their complexity, and different machines that recognize them, and you have the discrete finite automata, you have Poisson automata, you have the Turing machine, and then you have a whole super rich theory about computation. And computational mechanics makes a bridge between dynamics and information theory with all this other side of the world. And the idea here is that suddenly you start seeing things in a different way. So your data is not anymore created by the mechanism, but is inputs that you are feeding into the machine. And the machine is transitioning into different states. And according to, in the traditional way that this is used, is that you can recognize if my language is this string of symbols that I'm inputting is in the language or is not in the language. And based on the topology of the transitions, so now you have these are states, these are not the variables, these are variables, but these are states. So you start in this state, and then here, let's say it's a binary process. So whatever you add, this moves here. And then depending if you add a 0, it goes back to the first, but if you add a 1, it keeps going. And then if you add a 0, it goes back. But if you, so you can see that the different words, different strings that you're inputting generate different dynamics in this state, in this landscape of causal states. And this was the view that I was very interested to see how would emergence look from this perspective. And the intuition was about nested machines. So how could it be that you have a machine inside another machine? And how you operationalize that is the following. Let's say you have your machine is the small yellow arrow circles. And you have, in this case, you have 3 possible inputs, meaning you are at one state, let's say you are here. And based on the input, you are either going to stay in the same, or you're going to go here to this other guy or to this one here. And based on the 3 inputs, you're going to navigate over these many states. Now, let's say for some reason, you lose the ability to control the exact inputs. So either you input, let's say you have A, B, C. So you either input A or BC, but you don't have any more control of B or C. And what does it mean in the terms of dynamics is that suddenly you're going to have this stochastic dynamics. At some point, you don't know if you're going here or here. And this is sort of a problem because the theory of automata, the classic one, is about deterministic automata. So a natural question is, because I'm coarse-graining inputs, can I coarse-grain states such that the dynamic on the coarse-grained states is again deterministic? So you're sort of matching the coarse grain in inputs with coarse grain states. And suddenly, in this example, it works. So you can see that you are coarse graining states. So now the states are the big circles, and you have only 2 inputs. So before you had 3, A, B, C. Now you have 2, 0 and 1. You have the big arrows. And you see now you have a simpler machine that has less states and less inputs, but the smaller machine is working inside. And these 2 state machines are sort of working in tandem. And the hope of this is that if you have a very complicated machine, maybe you can explain it as a simpler machine first, and you understand the type of algorithm is running. And then you say, actually, I want to understand the details of the machine. And then you go one level down. Does it make sense? So this is the idea of computational closure. So a computing machine, automata, has a computationally closed level if there is coarse grainings at inputs and states such that I get another automata. This is another definition. And now, well, here's the definition. And now the picture that emerges is the following. You have a micro, and let's say you have 2 coarse grainings more. And each of these have different epsilon machines. And a good coarse graining would be one in which the epsilon machines are coarse graining of each other. And then you have sort of a commuting diagram, right? So either you, and you can also think that the epsilon machines are the theory of my data. So either you coarse grain your data and get a new theory, or you get a theory and then you coarse grain your theory. And the question is, are you arriving to the same place? And if the coarse graining is computationally closed, then the answer is yes. Are we good?
Would be equivalent to say that in figure B that the probability to generate a micro is the same if you rescale to the measure to the macro, but that's not the same.
Sorry, can you say it again?
Like it would generate a probability distribution for each state, but then in the coarse grain you'll have less states. But could you fit one probability into the other map when you cross grain?
It's a bit more than that because I wonder if any coarse graining has that property, but this is a very restrictive property. So only very specific coarse graining have this property. Because usually when you coarse grain and you do the epsilon machine the coarse graining, it might be a complete disaster. Like there might be not any mapping between the resulting epsilon machine and the original one. It could be even larger than the original one. So this is for specific coarse grainings where this thing holds. Yes.
Just a question. Can I think of the epsilon machine as some kind of effective theory including?
Yes.
Okay.
Yeah, that's exactly the idea.
Uh-huh.
And this has a bit of a renormalization flavor in the sense that you could think that the one below is quantum mechanics, that is super complicated, and then the coarse grain epsilon machine is sort of classical physics that is compatible with the one below, but has much less details and much. So that's sort of the similar flavor.
Then I have a follow-up question
Yes.
related to that,
Huh?
because in many cases the effective theory is not informationally close, maybe in this sense, but an approximation that becomes better and better as you increase the n. So, like, how do you account for this? That you have to take also some sort of thermodynamic limit?
Yeah, that's a good question. So far, the whole theory is very simplistic. So is perfect or none. And I very strongly believe that to make this practical and useful, we need to have this sort of approximations. And for the case of informationally close and computationally close, like it's very easy to say if this is almost zero, but it's pretty small, that you're almost informationally close. So it's easy to account for that.
But then it would say this is something that goes as like 1/n, where n is the number of variables you have, and something like that.
Yeah, so
You can do some sort of
true. So that n would be
micro.
yeah. So you're considering different macros and you're scaling them. That would be an interesting question. And then maybe with n, then the thing will go to zero. That could be an option.
There's one question in the June.
Mhm.
I think it's similar to what I'll ask, but when they say, I don't see a chance how I scale this to several levels.
Mhm.
So even through our match, so how, if you see a chance that this can scale to more levels?
To more than having one level.
Yeah.
Let me go to the next slide, and then maybe we come back to the same question. So the result here is that first, this commuting diagram that I mentioned already. So if you first run the epsilon machine of the micro and then coarse grain, or if you coarse grain and do the epsilon machine, you get to the same point. And the second important statement that is hidden in that lot of text is that information causal closure implies computational closure, and not vice versa, which was also a bit surprising for me. But the reasoning behind this is that causal closure and information closure depends on the actual probabilities. So it's very sensitive to the numbers of the probabilities, while computational closure is more of an algebraic property. And in that sense, there are many possible probabilities that will have the same type of transitions. So when you draw a diagram like this, or like this, or like this, there's no probabilities here. It's just like this is possible or not possible. And because of that, many different automata will have the same diagram and might have computational closure, but maybe some of them are causally close. So that's why one property is stronger than the other one. Now, with all that in play, the final sort of big picture is this. Let's say you have a system with 5 possible states, to make it very simple. So you can have 5 different states, and you have some complicated memory, non-Markovian, whatever. In the left, we have all the possible coarse grain. So we do brute force. And the diagram, the way to read it is the bottom one, you're not mixing any state. Then in the first level, you're mixing 2 states, so you end up with 4. The second level, you're mixing 3 states, so now 2 states, so you end up with 3, and then 4, and then 5. So in the top, you're confusing everything. So basically, you're not seeing anything. And that's all the possible coarse grain. Now, from those, we can highlight which are the causally close coarse grainings, which are the ones that satisfy the condition of causally close or informationally close. So let's say we test all of them, we measure this transfer entropy, and we keep only the ones that have 0. That's a sub lattice from the big lattice. And then we calculate the epsilon machine on each of them. And we are going to, because of the other theorem, we know that the epsilon machine of each of those processes is a coarse graining of each other. So they are again arranged in a coarse graining lattice. And it's interesting that sometimes you will have different coarse graining that have actually the same epsilon machine. So this is the simplest lattice of the whole thing. And my claim is that this lattice is sort of a bit of the blueprint of the computation structure of the system. And the way it works at multiple levels is because you can run the same story at every level. Like if you have one level, you can ask, do I have any coarse graining above me that is computationally close or causal close, etc. And you can keep doing it. And you end up with this type of thing. Now, computationally, I have no good, smart way to compute this in practice. I'm working on that, but at the moment, it's more of a theory where, of course, you cannot do this exhaustively. So for now, you have to be smart. If you have a system, you have to sort of guess which might be the good coarse graining. But hopefully, in the future, we'll have a data-driven AI, driven navigation. Yes.
I actually can say we published a paper this year on a very similar topic.
Excellent.
With a PhD student of mine, where we basically looked at dynamics of molecules, and we wanted to have an abstraction of this, such that in latent space they kind of have the kind of Markov chain structure, and we also use these information theoretic quantities as an objective to train this.
Excellent. If you can send me, I would love to read it. Thank you.
Sorry, can you say anything about how unique this thing on the right is? How much does it depend on the choices you make in between?
What choices?
So you make several coarse graining. You can choose how you make your clumps. So now you took these, you colored them green and orange and whatever. I mean, you could use a different coloring scheme or the different.
No, it is. This is brute force, and I'm not doing any choice. I'm trying all the coarse graining. And and out of all the coarse grainings, I'm keeping the ones that are informationally close. And then the theorem says that you should have a mapping like this that is not one-to-one. So basically, there's no degrees of freedom. Now, you cannot do this in practice in big systems.
Because your data tells you which ones are causing.
Yes.
But isn't it possible that there are 2 or 3 different routes that all have causally closed?
Yeah, and what happened, one interesting outcome of this is that we tend to think of these levels as a total order. And you have, like physics, chemistry, biology, and there's a single line. This theory shows you that sometimes you can have divergences. And like here, you have the epsilon machine, the micro, that is the most complicated one. You have 2 coarse grainings that are both computationally close, but they are not comparable. And that's sort of I still get a bit puzzled. What is the meaning of these 2 things? And then they come back again. One case where that happens that is quite simple is that your microsystem is actually 2 systems. You were not aware of that, but these are 2 systems running in parallel. Then you can, of course, coarse grain one or the other, and you get a sub-epsilon machine. So, but you will see also more general cases where you have some sort of non-trivial interaction. So my hope is that these anti-chains at different levels are going to give you some notion of compositionality. Like what are the parts of the system that are doing different things.
So you can always be sure that on the highest level, all the coarse grainings, all the epsilon machines end up at the same thing.
You can be sure because of this trivial coarse graining that is constant.
Yeah.
Or we have the epsilon machine that is one state that goes to itself. So it's not very interesting.
Yeah.
But you always have it. But what is actually not trivial is that, let's say you have a system that is a vector in the micro for some reason, you have an interesting process and an IID process in the second component. If your coarse graining keeps only the second one, you end up with an IID process that is not the trivial coarse graining, but if you try to build epsilon machine of an IID process, you get the top one. Because there is nothing to predict, there is no computation. So in that sense, by merging different coarse grainings in real space into theory space, you are sort of getting it right because these things might look different, but computationally it might be the same.
Maybe then can I repeat the question? Like if you have again a gas then you have like 6-dimensional space, and then you cross rank together. Yeah, okay. Thanks.
So I'll show some examples to illustrate the theory. One is the inverse diffusion model. I don't know if you're familiar with this. It is a very simple model from statistical physics. You have two chambers connected by a thin thing, and then you have a number of particles here, and with some probability they can move to the other one, and you have this super simple dynamic, classic statistical physics. And now the macro, the natural candidate, is the number of particles in the first chamber. And it happens that, lo and behold, it is computationally closed, informationally closed, constantly closed, etc. What is the meaning of this? It means that if I want to control the number of particles in the future, the best I can do is to set the number of particles before. It doesn't make a difference which is the particle that is here, the identity of the particles. So, I mean, and that is very simple, but it's a verification that this is work. So this says the dynamics at the level of the aggregation is completely independent on the level of detail. Now, this is sort of a simple example, but from an agent-based modeling situation, this is quite informative because if you want to simulate the dynamics of the aggregation, you might think that you need to simulate the whole system and you need to have these guys going here and keep track of everything. But it happens that if you're able to extract the dynamics of the macro, if you simulate the dynamics of the macro, you're going to get perfect simulation. You don't need to simulate the level below to get perfect simulation of the macro. And that is what computational enclosure means. So if you have a system that you're simulating, it's very useful to know which are the different levels, because then you can choose what is the level of simulation you want to do.
And here the upper level is the Markov chain,
The upper level is how many particles you have in each chamber,
which is a Markov.
which happens to be a Markov chain.
Yeah.
Yes.
So what happens with phase transitions? I mean, I'm just getting a bit annoyed how ideal things seem to be, like, because you're kind of saying, you know, physics, whatever, quantum, classical and stuff, and then there's many processes that we know that we need microscopic input to understand the macro level.
Yeah.
And phase transitions is one example of that.
Mhm.
That all scales start to matter at the phase transitions, effective theories, emergent effective theories break down, and this is related to that.
It's a bit tricky because I don't think that it's so easy to make the parallel, because here it's all about dynamics. Like, for example, if you have phase transition in an Ising model in equilibrium, there's no way to map that into the theory.
No,
Because
that's what I would agree with Jaden, the question. It could be at phase transition, all scales matter. There is no way to make any cost for any.
yeah, 100%.
Yeah, that's what I'm saying. So this is like regimes, you know, there's
Yeah,
something
no,
here
that is true,
can
that
be
is true.
like a regime
That is true.
where this can apply, but
And
it's not.
and it's funny.
Or do you want to say that, you know, this is how things are if it's emergence, and then
No.
if my conditions break down,
Mhm.
then it's not emergent.
So,
Because that would be, your conditions will break down at phase transitions.
100%. And there are very similar parallel discussions in neuroscience where some people say, oh, when the brain exhibits something like this is interesting. And some people say, no. When the brain don't exhibit this is interesting. Like when you have complete integration of scales. And I feel just having the ability to distinguish these different regimes is useful. And that's part of my point, that this is one view of emergence that some people embrace, where the whole is sort of less than the sum of the parts, you know. But that might be not the type of emergence you're interested in, and that would be completely fine. And then there are different types. I will present another type of emergence later.
But it's formulating the same question with the mass, because you're putting all internal process.
Hmm.
So what happens when the macroscopic states non-analytical? Then it's the same question that Jay made, but then maybe you can answer in terms of the machines.
Yeah, I don't know, but it's very likely that in different regimes you might have scales that are close, and then you go to criticality and then they disappear.
What you would see, I guess, is in this comparison of these three lattices, you would see that in the first step, you lose all coarse grainings except the bottom one.
Exactly.
And that will continue to survive.
Yep. Let me give another example that I find very illustrative to understand how this theory works. Here we have a network that is a modular network. So we have here 5 modules that are strongly connected within and weakly connected between. And we have a random walk. So we have a very drunk person in one node, and then is most likely to move to nodes within the community and less likely to move between communities. And to make everything very simple and symmetric, we have just two parameters. One is the strength of within, and the other is the strength between. And it's always the same. So that's the microscopic system. Now, my claim is the microscopic dynamic is going to be a Markovian process that is the exact position of the random walker at every time point. There is also a probability that the random walk stays where it is. That is this Q. Then the first level of description is in which community this drunk person is. And then you will have a dynamic between communities. And then there is a second coarse graining that is sort of funny. That is not which is your community, but what is the size of your community. So here we only have two types of sizes. We have communities of size, how is it, 25, and the other is size 9. And the claim is every level is computationally closed. And you can prove this mathematically. And it's because of the symmetry. If you start having different weights, then the thing breaks down. But because of the symmetry, if you want to have, and now this is interesting from the point of view of simulations, if you want to simulate the dynamics between communities, you don't need to simulate the dynamics at the micro level. If you manage to calculate the right probabilities, that's transition probabilities between communities, then that's perfect simulation. You're not wasting any level of precision by not running the level below. Another way to think of this is that you could implement this algorithm by first doing the next step at the macro level. So I'm staying in a community size 25. Then you say, actually, I'm staying in community A. And then you say, I'm actually staying in this node of community A. So you can run this sort of in a nested way. And you can stop at any point if you want to continue at the same level. And a final example, very timely, hoping that works. And is I hope you're all familiar with Hopeful networks today. Yeah, right. So in Hopeful networks, you are encoding these different memory states. Oh, wait, got frozen.
In your computer or in the screen?
The screen is not following my computer anymore.
Ah, okay, then wait.
What should I do?
Who's our expert internet?
Break it out internet.
Should I unshare?
That's what and see bottom is internet breaking down.
Oh, something with the internet.
Yeah.
Oh.
Yours? Oh, yes, there is a question.
It's the same one still, I think.
Maybe it's better to go in and out then.
Now what happened is that my edu-rom dropped,
Yeah. Ah, okay.
and yeah.
Can I ask you something about the previous example when you made the... So in the previous example, the random walk was just going from state to state, following a Markovian process, and then it could stay in some point. I mean, it was not a continuous time Markov process, just
Discrete.
what if your process was kind of continuous time, but the time that you stay trapped in some nodes is non-Poisson distributed? So it's like the non-Markovian process in some sense. Would then this would be computationally closed? Because I would imagine that then it would depend on which node you end up in within your community. That may drive like your process between communities as well. I don't know if you see.
Yeah, in that case, it might well, if the transitions between communities depend on the node where you are,
Exactly.
then it doesn't hold.
Then it doesn't.
For some reason, the other room doesn't work, so I will connect to my phone. So it's okay if I do 15 minutes more to do the other part is going to be much shorter.
Well, we can make it very long.
Fair enough. Up to you. All right, here we are. So in the case of hopeful networks, yes. So hopeful networks are these pins that are learning the different patterns. And one thing that you can measure is this dot product, the set number there. I don't know if you have seen this before. You have the P super mu is the pattern, it's a different pattern, and X is the actual state of your system. And that is the dot product of the state and the pattern, which is sort of the similarity. How similar is your actual pattern with the different possible destinations? And what you can show is that the dynamics of set are computationally close, in the sense that, and what the dynamic will look like is that you press play, you start from a random place, you start the dynamics, and the system will go to one of these 5 attractors. And from the level of dot products, it look like it's going to, in the beginning, all the dot products are going to be very small, but one of them is going to be a bit larger, and that one is going to start growing, and the other will keep down. And you can say, and the interesting bit is that the dynamic at the level of only these 5 numbers, that is tracking the similarity to each of the possible candidates, that is computationally close. So if you would like to know where the system is going, you don't need to keep track of individual neurons, but you just need to keep track of these global similarities. Yeah.
Yes, but this what you said work only in the retrievable phase.
Yes.
Because
Yes.
in the
Yes.
non-retrievable phase, it
100%.
breakdown.
100%. Would be interesting to see if the non-retrievable phase has any.
Because they
Focus,
happen with the spurious state and the interference between the pattern, then
Yes,
it's not computationally close anymore.
I mean, this will not work, but maybe there's another description. Because of the limitation of the theory, now you can have this sort of ansatz, and then you can prove it or not. But oops. Excellent. Okay, so to summarize this approach, we have this view of emergence based on computational closure that is about self-containment. And you might not like it, and that's fine. It isn't not your view of emergence. That's perfectly fine. It's a very specific way where you have emergence in the system, where you have this level that is self-contained, that has its own rules. That's sort of the vision. And why you could find it interesting for 2 reasons. One, for the system itself, it enabled these decoupled levels that are amenable to controllability. So, for example, an interesting conjecture is that living systems maybe need something like this. Like we are like that. We are a macroscopic system instantiated in physics, but we work at a higher level. We don't have control on, microphysics, but we survive. So maybe we couldn't survive if we would not have a self-contained level at the macro level. Now, for the researcher, if you're doing simulations, it could be very helpful to have a knowledge of this architecture, because with that you could choose the level of simulation details that you want to run. And maybe there are other, yes?
There's also a question from this one. Casper asked if you could comment on the frameworks that exist on emergence that relates to what you say. He mentioned Mars 3 level of organization.
Yeah, I mean, there is a lot of work in similar direction. The Mars is a tricky one, because Mars, the levels are quite distinct of quality of each other. I don't know if you're familiar with Mars. There is a computational level, that is what the system is trying to do, is sort of teleological level. Then you have the algorithmic level, that is algorithm that is running, and then the implementation level. So this is sort of, I think there is some discussion in the discussion section of the preprint, where there is something about the algorithm and the implementation that is sort of related, but there is not a qualitative distinction between Z and X. It's just a corresponding of each other. So yeah, and so there is a lot of work in similar directions, but capturing exactly this, I'm not aware of other. And yeah, if he has a specific other ones that we'd like to discuss. But I would like to go, sorry, I don't go too much in detail, but I would like to go to the other framework so we can have this comparison. So whole minus part, and let's see now in a situation where the whole is more than the sum of the parts. I want to have sort of the contrast. By the way, that's a real photo. These are real birds making a macro bird. It's really interesting. So here, the scenario is going to be the following. We have a micro, but now, importantly, the micro is going to be a vector. In the other case, we were not thinking about parts of the system. The micro was one thing with many states, but we never thought about the parts of the micro. Here, we're going to have specific parts that are designated from 1 to n, and we have time evolution of this vector. And we're going to have, again, a coarse graining. To make life simple here, we're coarse graining a given moment without memory. And then we have the dynamics inherited at the coarse grain level. And we're going to try to come with ideas of causal downward causation, that is how the collective property could affect the micro, or causal decoupling, that is the collective property affect itself without intervention of the one below. And the idea here, this is based on a whole framework that is called partial information decomposition, that if you're interested, I'm giving a talk tomorrow in the science part at 11. So I will not explain what partial information decomposition is, but intuitively, the idea is that you can measure unique information, like how much information is unique from this variable about this other variable that is not contained in these other variables. And the definition here is V, the coarse graining, is emergent, has an emergent quality if it gives unique information about the future that is not given by the parts of the micro. And if you're very picky, you're going to recognize that there is something weird about the definition, because the micro has more information than the macro, because the macro is a coarse graining, so I'm losing information. And now I'm claiming there is some information in V that is not in X. And you would say, no, how can that be? And the trick is that the conditioning is not with respect to the whole vector, but with the parts of the vector when you see them separately. So you look how much information is in X1 and not in the others. And then how much information is in X2 and not in the others, how much information is in X3 and not in the others, etc. And it happens that because of information theory magic, there is some information theory in the joint that is not in the parts. And that is what could be being captured by V. And that is when things work. In information decomposition, we call that synergy. Whenever there is information in the joint that is not in the parts, and implicitly, the definition is not explicit about it, but implicitly saying if V is capturing synergy with respect to the future, then that is when emergence comes in.
What is the meaning of this? With the UN.
Unique. So he's saying when V has unique information about X measured at T prime that is not in X1 at T, X2 at T, etc. And there is a whole mathematical formalism that I can explain tomorrow. But just believe me that there is a way to measure this from data. As a minimal example of how emergence could look like in a very, very simplified setup, here we have two binary processes. And the rule is the following. You start with some random initial condition. So you flip two coins, and here they end up being both heads. So now the rule is, if they're equal, they're going to keep being equal with very high probability. But equally white, equally black, I don't care. So you preserve the similarity, but not the actual state. And at some point, they might flip. So here they are flipping between equally white to different. And then with high probability, they are going to keep being different. But if they're different, black and white or what, or the other side, you don't care. So basically, the system is propagating the parity, the similarity, but it's not propagating the actual state. And you can prove that if you are X1 and you are in state white in the time 0, and I ask you, what can you tell about the future? You tell nothing. You have no idea what is going to happen. So you have no ability to predict or to push or to pull anything. If I ask X2, given your state, what can you say what will happen? You have no idea. But if you ask both of them, they can predict something. They can say, oh, we are going to stay the same. We don't know if we're going to flip or not, but if we are the same, we are most likely to stay the same. So that is the type of phenomenon that this is trying to capture. Here, the V would be the parity, so an XOR of both. And that XOR is very informative of what is going to happen, but that information cannot be found in the first part or the second part, can only be found in both. Does that make sense? Of course, this is a very artificial scenario. I'm not claiming that nature has this type of things, but this is an extreme case that is simple to reason about. And now the beauty of this theory is that so far that's a definition. Out of that definition, you get three theorems. The first is, although the definition of emergence is based on this unique information, you can, the partial information decomposition has these ways of measuring synergy, and you can prove that synergy is the capacity to have emergence. So you might not know what is the V that is emergent, but what this is saying is that if you have just the dynamics and you measure the synergy within the dynamics, there is a if and only if. If there is synergy, there exists some V, even if you don't know which is it. So synergy is the capacity to have emergence in the system. And this is sort of the intrinsic property of the dynamics that allow for this to happen. This is the first theorem. Second theorem is use more math and says, if you go into the crazy story about information decomposition, there is a way to decompose synergy into two sub-synergies. And that will give you something about downward causation. That is, when this synergistic information is telling you something about specific parts. So for example, if you have a spin system, is this XOR going to determine the state of this spin in the future, which we would call downward causation? So a collective property is determining the future of parts. Or maybe the XOR will affect the XOR. That is the example I showed before. It's not affecting any individual spin, it's affecting a collective property. And that is what we call causal decoupling. So there is this thing that is operating at a different scale without affecting below. So far, this is all math and all very technical and all very hard to compute. Yes.
Sorry, I have a question here because I'm not sure the fact that XOR would be a relevant variable means that this necessarily is a notion of emergence. So that's the thing I do not understand, because to me it's more like we are not observing the relevant variable here, rather than we are observing an emergent phenomenon.
Really true. The XOR is a pedagogical tool, and I'm not saying emergence is XORs. I'm saying emergent is XOR is a toy model that satisfies this, but there are other systems that are going to show it. And I will show some examples with this.
No, but I mean, I don't think so. The fact that we are observing the system it would be like we are measuring the.
I know.
We're making an experiment, we're measuring a partial number of variables, and the actual relevant variable is not measured.
I know what you mean. So what you say is that the relevant variable, you should have to do a change of basis.
Exactly.
Yeah.
And that's not saying.
But let's discuss that in an example. So far the XOR is just for illustration, but I completely agree with you that in some cases, if you're measuring some variables, maybe those are the wrong parts. And the dynamic happens in a different type of parts, and you have to do a change of basis, and then the emergence goes away. Completely true. But let's discuss that in the example. And so far this is math, and so far all of this is very hard to calculate. But the good news is that there is a third theorem that says if there is this condition that is sufficient but not necessary, that means if the condition is satisfied, you have emergence. If it's not satisfied, it's inconclusive. But the condition itself is very simple. And what it says is you have a candidate V, you measure the mutual information between V and different time points, so sort of the autocorrelation, how much you can predict for V based on V. And then you measure how much you can predict about the future V from the parts. So let's say you have this spin system and V is the energy, and given that the first spin is up, what is the most likely energy state for the next state? And then given that the second spin. So you do all pairwise predictions from parts to the whole thing. And what you're trying to do is you're trying to explain away the predictability of the macro with the macro from the micro. And the question is, can you explain that away or not? And if you cannot, so if you can explain more about the macro from the macro than from the micro, then that's a sufficient condition for this type of emergence to happen. And this is not necessary for this following reason. It could be that the x's, the different parts, are correlated, and the predictive ability, we're double counting it. Because maybe x1 and x2 are equal. And then we are saying x1 predicts 3 bits of b, and x2 predicts the same 3 bits. And so then we have 6. But we shouldn't do 6, we should do 3. But because this is very simple-minded, we are double counting, and we're okay with that. Because by doing only pairwise correlation, pairwise statistics, we can measure this in pretty large systems. So here we don't have coarse dimensionality. Even if you have the game of life with a lot of cells, you only need to measure pairwise statistics to compute this. And this is interesting because then you can estimate this in bigger systems. Yes.
I'm trying to see the difference between this and what you said before.
Yeah.
Because you have here the information between the macro and the macro minus the information with the micro and the macro, which looks like that if that should be 0, the difference, it's information close.
That's a fantastic question. So the difference is subtle. Is the second term, if it would be not the sum over the parts, but the whole thing, the mutual information from the whole vector x to v, then it will be the same.
Because you make it from subsets of the micro.
Yeah.
So this depends on your choice of parts.
Yes. And that's why if you, let's say you want to measure emergence in the Lorentz butterfly, what are your parts? Are you going to take X, Y, Z? Like, so then you shouldn't use this.
But also, how about the feasibility of measuring these? Because in a system of n state, you have to check all the partitions to choose your.
You don't need to check partitions. You need to check each of the parts. So if you have the brain, 100 brain regions, you need to do 100 computation. That's it.
Sorry, it's not that you get subset of the line.
That's an interesting question. So this is emergent of level 1. So you are emerging with respect to single parts. But it could be that the information is in dyads, is in links.
That's what I understood.
So if you want to say, I want to see if it's emergence of level 2, then you want to check the links. Then the sum should be over the pairs. And then this condition is more difficult to satisfy. And then you can go toward a 3, 4, 7, whatever, and then it becomes computationally more complicated. So in theory, you can do all those corrections. You have 2 problems. One is that estimating the information theoretic quantity is going to be more difficult. And second is that double counting is going to get worse. But you could still try. Does it make sense?
Yeah, it was more like I understood you present this way because it means like your microstate is not necessarily causing the macrostate. You would find the right cross grain by checking.
Yeah, no, that's yeah, no. In principle, you could have a V that is emergent at the level of single parts, and then you start trying 2, 3, 4, and at some point it would break, and then you could say, oh, this is emergent at level K. So that would be pretty interesting to say at what point this thing breaks. Computation is quite hard to do it, especially in large systems, but in principle, this is something you could investigate. But the key point is what was saying, that here, this is critical, what are the parts? And for example, if you study a flock of birds, it's reasonable that the parts are the birds. But if you study the Lorentz attractor, it's not clear what are the parts. So in some systems, you shouldn't use this. But in some systems, when you care about specific parts, if you have a social system with people, it makes sense that you don't want to do any combination of people, right? And you care about specific partition. So let's go with some examples. So in the game of life, this is something we can calculate. And what we did was a funny experiment. We have a game of life system, and we made collisions between particles because we have some knowledge of the game of life. We know gliders and we know other things. And we know that sometimes you put 2 gliders and they collide and they create something else. So what we did was B is a vector that is identifying specific type of particles. Like, do you have a blinker? Do you have a glider? And then if you have one, at least one, you have a 1, and if you have none, you have a 0. So the question was, you want to predict the outcome of a collision, which are the identities of the particles after the collision, and you want to do that prediction based either on what are the identities of the elements before, or the actual states of the cells, but each of the cells separately. So you ask the cell number 1, what do you think is the outcome of this collision? They say, I have no idea. You can predict 0.1%. But then you sum all of this little predictive ability of each of the cells and you sum it up. With that, you get the first term. And then you do the prediction from identities to identities. Like given that the initial condition has a blinker, what is the outcome? And it happens that you do a better prediction by knowing the identities than by knowing the states of the cells separately. Does it make sense? Because one single cell, it tells very little about the outcome of the collision at the level of particles, right? So that is the idea. Of course, if you now start looking for sets of order k, that's going to become more difficult to be satisfied. But this is saying at the level of single cells, you cannot predict well the identity after the collision. Second example, flock of birds. So this is all these mathematical flock models that I'm sure you're familiar with. So here we have a parameter that is the avoidance strength. In one case, you have these military birds that are very strictly following each other. In the other case, you have completely random birds that are doing whatever they want. In the middle, you have a mix. And you have a red dot, I hope you can see, that is the center of mass. So the question here was, do the center of mass have emergent dynamics?